what we've tried to do up to this point in presenting the chem study is start simple and go to the more complex. So in the chem study order, what we're looking at is elements and atoms and fundamental particles. And then molecules and compounds. And that will evolve into reactions and states of matter and solutions and chemical reaction studies and some more and more complex systems. But this is where we are right now. So we've just completed looking at the classification of elements by the periodic table and how to define just the basic structural composition of an element from the periodic chart. Now we want to look at what molecules are. Molecule is a generalization for a single molecular structure where it consists of two or more parts. And compounds represent a whole lot of that same structure. So it's semantics more than anything in this, and when we talk about molecules and compounds. Okay, so we defined the atom as the smallest entity in elements, smallest entity of a substance. Remember, substances are homogeneous in nature. Smallest entity of a substance that cannot be broken down by heat, light, and electricity. But when we go into the molecules, it's the same definition, they're the smallest entity of a substance, but they can be broken down by heat, light, and electricity. So we start with the definition of molecules. And compounds. The smallest that can by chemical or physical methods. And so that's heat, light, and electricity. Now, if you look at the handout that I gave you, it gives you kind of a classification of the types of compounds in the universe and how they are generally put together. Okay. So we start with a classification of compounds and molecules. Well, in general, a molecule is a substance that fundamentally contains two or more elements chemically combined and has its own chemical and physical properties. So compounds and molecules are substances consisting of two or more elements chemically combined and have unique chemical and physical properties. So, and of course, it represents zillions of substances that are floating around in the surface of the earth and in outer space or wherever. And so we need a better way to study these instead of some conglomerate nebulous collection of particles. And so molecules in general and compounds are divided into two broad categories. In general, they are ionic compounds and molecular compounds. As you study the chemistry, it's very important that you keep in mind how the course is evolving so that you can study simple issues and then build them to the more complex. Ionic compounds consist of two or more elements chemically combined, as you would expect. But these two or more parts, one is a metal and a non-metal component. Is the foundation of the ionic type systems. Molecular compounds are two or more non-metals. Of course, also chemically combined. So now we're beginning to break them down into something that are easier to study. Now, when elements combine chemically, they combine in definite proportions by mass. And as an example, in combinations in water, for example, formation, we have hydrogen and oxygen, molecular hydrogen, molecular oxygen combining to make liquid water. And we have to balance it with something like that, a coefficient we'll talk about later on. But in the substance generated, when we talk about water, it always combines in a 2-to-1 ratio. That means it has a unique chemical composition or unique percent composition. That says composition, if you want what the scribble means. And as always, two hydrogens and, let's keep that up, two hydrogens and one oxygen, as you expect, like that. So anywhere you find a compound that has two hydrogens and an oxygen, it's most likely water. And what you need to learn how to do at this point is determining the percent elemental composition. That is, what is the percent of each element that makes up that compound? And it's always the same for that given compound. And there are many compounds out there that have the same percent compositions as you go through them. But that one compound is always in that percent composition. Now, the way you deal with this is using percentage of hydrogen and percentage of oxygen relative to the molecular weight. And if you know mole weight of compounds is equal to sum of the atomic weights. So the mole weight of H2O will be based on two hydrogens plus one oxygen, and that is equal to, I always round them up to the nearest whole number. It's just simple. You can add decimals into the atomic numbers if you want, but it just moves faster. 1 plus 2 times 1 plus 1 times 16 and is AMUs at this point. Atomic mass units, we mentioned that when we talked about isotopes in the last lecture. Anyway, this gives you 16, 17, 18 atomic mass units for the formula weight of H2O. Well, the percent hydrogen in the H2O is the mass of all the hydrogen divided by the mass of the molecule times 100. So we have 2 hydrogens over H2O times 100%. So that's 2 times 1 over 18 times 100%. And that is, I'll say 11% by weight. And same way with oxygen. Now you can calculate the rest of this. The oxygen, 100 minus 11, give you 89%. Or you can go 1 oxygen, I'll put parentheses to emphasize it, over the formula weight of whatever the compound is, times 100%. And that's 1 times 16 over 18 times 100%. And that's 89%. So that's just quickly giving you the method that is used to calculate percent compositions. And we'll do another one here. Here's 3 elements in the compound. What's the percent of hydrogen, sulfur, and oxygen in this formula? Well, the formula weight, of course, is 2 hydrogens, 1 sulfur, and 4 oxygens, which is 2 times 1 plus 1 times 32 plus 4 times 16, and all comes out in atomic mass units, and it turns out to be 98. I just happen to remember that one. Atomic mass units when you add them up. Everybody good on that, I hope. Okay, so we take each one of the elements, hydrogen, sulfur, and oxygen, and apply the percent definition, part over total times 100. And so your hydrogen is, we got a 2 times 1 over 98 times 100%. And then sulfur is 1 sulfur, 1 times 32 over 98 times 100%. And then we have 4 oxys, 4 times 16 over 98 times 100%. So that's what I got. I'll back me up. Now, when you do your set of percentages and you want to check your work, when you calculate the percent composition in this manner, you can the sum of the percentages always equals 100%. Or 99.999 or something like that. So 6531 plus 32.65 plus 2.04 gives an even 100%. So that just kind of allows you to check your work to see how it works. Now you'll find you'll need to define percent composition of an element or 2 elements or so as you go forward in the work in chemistry, and this is a common calculation. So second part of this is to give you the basis of writing chemical formulas and using basic rules to name chemical compounds. A chemical formula can come in many forms. There are molecular formulas, structural, empirical, stereographic, and so forth. And our interest right now will revolve around the empirical and molecular formulas is what we'll be working with. Typically, a chemical formula consists of a positive component and a negative component. Now, the reason I don't use elements is because some of the components are polyions, and we want to keep that in mind, that the negative component of some compound is really a molecule that's floating around with a charge on it. We'll emphasize that. So, in writing any chemical formula, you have to take into account the positive and negative structure. Now, these are called oxidation states, or charges on the elements. And rule 1 for neutral molecules the sum of all charges equals 0. And I'll emphasize that. That means if you apply the oxidation states or charges on elements and polyions and add them up relative to how many there are within a formula, the sum of those charges will equal 0. And that verifies the accuracy of your formula. If you have a polyion that is the sum of the charges equal a net oxidation state or charge. For example, if you were talking about the ammonium polyion, its net charge would be a +1. If you're talking about the nitrite, we'll use that one, or nitrite is an NO2, its overall charge is negative, and then sulfate is a -2 or 2-, however you want to. But the elements within this structure have what they call formal charges, and the sum of all those formal charges gives a net charge, and that's what this refers to. Now, we will learn about how to go about determining what the formal charges of each element is when we get over to chemical bonding. But for right now, a molecule that's carrying a charge is a net charge and is classified as a polyion and is the positive or negative fragment of the molecule. Okay, empirical formula is the smallest whole number ratio of elements in a compound. Whereas the molecular formula, and I'll give you examples when I finish this. The molecular formula is the actual whole number ratio of elements within that compound. Let's say you're given this formula. CH2. And you cannot reduce the subscripts to smaller numbers. In other words, you can't go through and divide by 2 and get something less complicated. And so this is the smallest whole number ratio between carbon and hydrogen for whatever we're working with. And this is the empirical formula of what I'm going to make a molecular formula for. Now, there are compounds where the empirical formula and the molecular formula are the same, but I'm using one that's not. So sometimes the empirical is actually a molecule, and sometimes it's not. This is not. Okay, so carbon doesn't combine with just 2 hydrogens. We'll get to that in the future. But if I come over here and write this, that is a true molecule. That's called ethylene. It is a molecular formula. So if you were talking about ethylene, the actual whole number ratio is 2 to 4 for that molecule. But the empirical ratio for that is a 1 to 2 for the carbon and hydrogen. That's what I'm trying to define, to show you what empirical means against what molecular means in terms of what we're trying to talk about today in formulas. Now we'll learn how to take percent compositions of elements in a compound and determine the empirical formula and molecular formula. So there's a little procedure that I teach students when we get over into calculations in chapter 4. And so we'll save that part till we get there. Now you should stay close to a periodic table and one in the book, or have one that you've inserted into your notes, or something you can pull out and look at as we go through this. When we look at the periodic table, step 1 is what are the general classifications of elements as you just glance at it. Well, if we look at the diagonal, the little staircase we've been talking about, elements on the right of that staircase are nonmetals, and elements in the green, as you see here, are metallic in nature. And all the details of it is irrelevant right now. What we need is just, okay, metals on the left, nonmetals on the right. So in writing an ionic compound, first of all, is a metal plus a nonmetal. So, to write the compound, we need to pick an element in the green portion over here on the left, and then something over here on the right of the blue lines, and put those 2 elements together such that the sum of charges equals 0. You know what I said? Pick something on the left, stick something on the right, and hook them together such that the sum of oxidation states or charges, net charges, equal 0. So if I pick on the left side a sodium, for example, well, sodium right here is in group 1, so it has 1 outer shell electron. So it's going to have a tendency to lose 1 electron. And so its oxidation state and writing compounds is a +1. Okay? And pick something over here in the purple. We'll pick something out of the halogens right here, this first 4 halogens, fluoride, bromide, and iodide in there, because all of those have 7 outer shell electrons. So its tendency is to gain 1 electron naturally by the path of least resistance thing we talked about. And so that would make everything in that column 7 halogens a -1. So I could put Cl just as an example, and I know that its oxidation state is going to be a -1. And so when I hook these together chemically, Na bonded to Cl, what I want is a +1 plus a -1 to be 0, and of course it is. And so that verifies the number of elements of each type that you need to make a legitimate formula. Now, ionic compounds, you reduce the subscripts to the smallest whole number ratio. But in molecular compounds, that's not the case. I'll show you the difference when we get to the molecular compounds. Now, what if I picked magnesium and sulfur, magnesium sulfide? Now, magnesium is in group 2 on the periodic table. If you can see this, is right here. And sulfur in the same row is over here in the purple, right here. And it has 6 outer shell electrons, so what would its oxidation state be? -2. So we want to combine that with sulfur -2, and we hook those together. Magnesium sulfide is what is formed, and we have a +2 and a -2 going together, and it would seem that we might put subscripts like 2 and 2 of each one. Sometimes some people may remember being taught that if you take the oxidation states and swap them, you can have those as subscripts. But this has to be reduced to smallest whole number ratio, so you divide everything by 2. This would be the appropriate formula, a 1-to-1 combination, to make it simple. Okay, just to emphasize that again, what if we had, let's see, let's try zirconium, which is a +4 oxidation state. It's one of those fixed charge elements I was telling you about. If you go in there, it's number 40 on the periodic table. And we'll pick oxide, zirconium oxide. A nice blue crystal when it's all said and done. So it's a -2. So in putting this together, you would need a couple, 2 oxygens to hook up with the zirconium. That's an R, believe it or not. Zirconium. So I would have to use 2 in this ionic formula, and to get zirconium oxide, and I would have 2 down here. I'd have to have 2, and I would have to have 4. I'd put a 4 down here where you're swapping the coefficients like that, because what you're looking at here is 2 times +4 plus 4 minus 2's, and what that would give you is 8 minus 8, or 0, which verifies, yeah, that's really what it is. The structure is, and we will talk more about this when we get to bonding, the structure from the numbers is 2 zirconiums and 4 oxygens. But since this is an ionic compound, the rule is reduced to smallest whole number ratio. That's the appropriate presentation of the formula. And so the correct formula for the zirconium oxide would be ZrO2. That's the correct formula, and because it's an ionic compound, metal, nonmetal, and reduces to smaller whole number ratio. So now we look at polyions in ionic compounds. This will become very important when we get over into chemical equations, especially what we call metathesis reaction, or ionic double replacement reactions. Here, the polyion retains its formula and ionic charge. For example, if you have sodium plus 1 and you're combining it with sulfate, which is a -2, okay, the sulfate has to stay together, including the subscripts and charge. Stays there. So when I hook this together, sodium and sulfate, what we're looking at is a +1 and a -2 for the entire SO4 structure, as you remember from your polyion quiz. However, the sum of the oxidation states does not equal 0, so I have to increase this to 2. Now, when you're writing formulas to increase the element, you use subscripts. Now, we will use coefficients when we write equations to increase or decrease, but that including the subscript says, okay, this is the formula for sodium sulfate, and there is no other that would match that. So you have to have and +1 and all of it must equal 0 to verify the formula. So you have 2 sodiums and 1 sulfate. Now it's very important that you be able to look at an ionic compound and separate it into its cationic component and anionic component. How about something like this? Potassium Cr2O7. That's potassium dichromate. How do you know what the positive component and the negative component is in that formula? This is a rule that I tell students, and it simplifies it. When you look at the formula as written from left to right, isolate mentally the first metal in that structure. Everything else behind that first metal is the polyion. And this, of course, is the cationic component. And so if you put it into water, for example, it's a salt. The word ionic compound and salt are synonymous. They're the same words. Okay, so if I put this into water and make an aqueous solution out of it, it would ionize 100%. Well, it should have a subscript of 2 right there. So when it breaks apart, it breaks into 2 potassiums and 1 dichromate, like that. So it's very important that you recognize that, because what's going to happen is this is going to react with something else and become a potassium chloride, and that may become a lead chromate out of some other reaction later on. And it's very important that you be able to recognize how to separate the positive and negative components in the formulas that are written. And there are some notation issues that you need to take into account. Say you have ammonium ion and phosphate, like that. Now put those together into a formula. So you would have an ammonium ion and a phosphate that would hook together, NH4. You have to keep everything together there, and a PO4 together as a particle. You look at it as an individual particle, but that particle has a -3 charge, or the particle has a +1 charge. Now this is a +1, this is a -3. Obviously the charges do not add up to 0. So what does that tell you to do? You have to have 3 ammonium ions. Well, if I put a subscript 3 down here without doing anything else, obviously it's 43 hydrogens. Wrong. So we use parentheses in there to isolate that. And we only need 1 -3 to give us the appropriate charges on the compound, and defines the number of positive and negative components in that compound. Now the Ammonium ion is a unique structure. If you look in, it's the only non-metallic polyion you have. And when it goes into solution in compounds, it breaks at the ammonium. So what I'm telling you to do is pay attention to the NH4 structure and get that in your mind, because if you have a formula, say NH4OH, how do you ionize that structure? Well, you recognize NH4, and it, like metals, and it's the only one that'll do this for right now, as you know. Any other compound would have a metal right there, like sodium hydroxide. Well, yeah, the hydroxide is the polyion, but here it is the only cationic polyion you'll have to deal with, and it's NH4 plus OH is the ionization, and it's a 1-to-1, as well as this sodium and hydroxide come apart. Sum of charges equals 0 for those. So be aware of parentheses where you'll need, because you insert those to, at least isolate the particles. And then be aware of ammonium ions as the only cation that will come out of the structures.